Hey Internet, so I'm sure you've heard all the buzz about artificial neural networks and deep learning, and you probably think it's all really complicated. But keep watching, and I'll show you that it's actually a lot simpler than you might think. We'll start off by talking about how we think your brain works, and how that inspired the development of artificial neural networks, and how those artificial neural networks have evolved over time to be what they are today. And we actually have some hands-on activities where you can dive into your own neural network and play around with it, and you'll end up with a really intuitive sense about how these things work. It's not as hard as you think, so let's dive in. Let's dive into artificial neural networks and how they work at a high level. Later on, we'll actually get our hands dirty and actually create some, but first we need to understand how they work and where they came from. So it's pretty cool stuff. I mean, this whole field of artificial intelligence is based on an understanding of how our own brains work. So, over millions of years of evolution, nature has come up with a way to make us think, and if we just reverse engineer the way that our brains work, we can get some insights on how to make machines that think. So within your brain, specifically your cerebral cortex, which is where all of your thinking happens, you have a bunch of neurons. These are individual nerve cells, and they are connected to each other via axons and dendrites. You can think of these as connections, wires, if you will, that connect different axons together. Now, an individual neuron will fire or send a signal to all the neurons it is connected to when enough of its input signals are activated. So at the individual neuron level, it's a very simple mechanism. You just have this cell, this neuron, that has a bunch of input signals coming into it, and if enough of those input signals reach a certain threshold, it will in turn fire off a set of signals to the neurons that it in turn is connected to as well. But when you start to have many of these neurons connected together in many different ways with different strengths between each connection, things get very complicated. So this is kind of the definition of emergent behavior. You have a very simple concept, a very simple model, but when you stack enough of them together, you can create very complex behavior at the end of the day. And this can yield learning behavior. This actually works. And it not only works in your brain, it works in our computers as well. Now think about the scale of your brain. You have billions of neurons, each of them with thousands of connections. And that's what it takes to actually create a human mind. And this is a scale that, we can still only dream about in the field of deep learning and artificial intelligence, but it's the same basic concept. You just have a bunch of neurons with a bunch of connections that individually behave very simply, but once you get enough of them together, wired in enough complex ways, you can actually create very complex thoughts, if you will, and even consciousness. The plasticity of your brain is basically tuning where those connections go to and how strong each one is. And that's where all the magic happens, if you will. Furthermore, if we look deeper into the biology of your brain, you can see that within your cortex, neurons seem to be arranged into stacks or cortical columns that process information in parallel. So for example, in your visual cortex, different areas of what you see might be getting processed in parallel by different columns or cortical columns of neurons. Now each one of these columns is in turn made of these mini columns of around 100 neurons per mini column that are then organized into these larger hypercolumns. And within your cortex, there are about 100 million of these mini columns. So again, they just add up quickly. Now, coincidentally, this is a similar architecture to how the video card, the 3D video card on your computer works. It has a bunch of very simple, very small processing units that are responsible for computing how little groups of pixels on your screen are computed at the end of the day. And it just so happens that that's a very useful architecture for mimicking how your brain works. So it's sort of a happy accident that the research that's happened to make video games behave really quickly or play Call of Duty or whatever it is that you like to play lent itself to the same technology that made artificial intelligence possible on a grand scale and at low cost. The same video cards you're using to play your video games can also be used to perform deep learning and create artificial neural networks. Think about how better it would be if we actually made chips that were purpose-built specifically for simulating artificial neural networks. Well, it turns out some people are designing chips like that right now. By the time you watch this, they might even be reality. I think Google's working on one as we speak. So at one point, someone said, hey, the way we think neurons work is pretty simple. It actually wouldn't be too hard to actually replicate that ourselves and maybe try to build our own brain. And this idea goes all the way back to 1943. People just proposed a very simple architecture where if you have an artificial neuron, maybe you can set up an architecture where that artificial neuron fires if more than a certain number of its input connections are active. And when they thought about this more deeply in a computer science context, people realized that you can actually create logical expressions, Boolean expressions, by doing this. So depending on the number of connections coming from each input neuron and whether each connection activates or suppresses a neuron, you can actually do both. That works that way in nature as well. You can do different logical operations. So this particular diagram is implementing an OR operation. So imagine that our threshold for our neuron was that if you have 2 or more inputs active, you will in turn fire off a signal. In this setup here, we have 2 connections to neuron A and 2 connections coming in from neuron B. If either of those neurons produce an input signal, that will actually cause neuron C to fire. So you can see we've created an OR relationship here where if either neuron A or neuron B feeds neuron C 2 input signals, that will cause neuron C to fire and produce a true output. So we've implemented here the Boolean operation C equals A or B, just using the same wiring that happens within your own brain. And I won't go into the details, but it's also possible to implement and not in similar means. Then we started to build upon this idea. We created something called the Linear Threshold Unit, or LTU for short, in 1957. This just built on things by assigning weights to those inputs. So instead of just simple on and off switches, we now have the ability, the concept of having weights on each of those inputs as well that you can tune further. And again, this is working more toward our understanding of the biology. Different connections between different neurons may have different strengths. And we can model those strengths in terms of these weights on each input coming into our artificial neuron. We're also going to have the output be given by a step function. So this is similar in spirit to how we were using it before, but instead of saying we're going to fire if a certain number of inputs are active, well, there's no concept anymore of active or not active. There's weights coming in, and those weights could be positive or negative. So we'll say if the sum of those weights is greater than 0, we'll go ahead and fire our neuron off. If it's less than 0, we won't do anything. So just a slight adaptation to the concept of an artificial neuron here, where we're introducing weights instead of just simple binary on and off switches. So let's build upon that even further, and we'll create something called the perceptron. And a perceptron is just a layer of multiple linear threshold units. Now we're starting to get into things that can actually learn, okay? So by reinforcing weights between these LTUs that produce the behavior we want, we can create a system that learns over time how to produce the desired output. And again, this also is working more toward our growing understanding of how the brain works. Within the field of neuroscience, there's a saying that goes, cells that fire together wire together. And that's kind of speaking to the learning mechanism going on in our artificial perceptron here, where if we have weights that are leading to the desired result that we want, you can think of those weights again as strengths of connections between neurons. We can reinforce those weights over time and reward the connections that produce the behavior that we want. Okay, so you see here we have our inputs coming into weights just like we did in LTUs before, but now we have multiple LTUs ganged together in a layer, and each one of those inputs gets wired to each individual neuron in that layer, okay? And we then apply a step function to each one. Maybe this will apply to, classification. Maybe this would be a perceptron that tries to classify an image into one of 3 things or something like that. Another thing we introduced here is something called the bias neutron off there on the right. And that's just something to make the mathematics work out. Sometimes you need to add in a little fixed constant value. That might be something else you can optimize for as well. So this is a perceptron. We've taken our artificial network, moved that to a linear threshold unit, and now we've put multiple linear threshold units together in a layer to create a perceptron. And already we have a system that can actually learn. You can actually try to optimize these weights, and you can see there's a lot of them at this point. If you have every one of those inputs going to every single LTU in your layer, they add up fast, and that's where the complexity of deep learning comes from. Let's take that one step further, and we'll have a multi-layer perceptron. So now instead of a single layer of perceptrons, of LTUs, we're going to have more than one. And we actually have now a hidden layer in the middle there. So you can see that our inputs are going into a layer at the bottom, the outputs are a layer at the top, and in between we have this hidden layer of additional LTUs, linear threshold units, that can perform what we call deep learning. So here we have already what we would call today a deep neural network. Now there are challenges of training these things because they are more complex, but we'll talk about that later on. It can be done. And again, the thing to really appreciate here is just how many connections there are. So even though we only have a handful of artificial neurons here, you can see there's a lot of connections between them, and there's a lot of opportunity for optimizing the weights between each connection, okay? So that's how a multi-layer perceptron works. You can just see that, again, we have emergent behavior here. An individual linear threshold unit is a pretty simple concept, but when you put them together in these layers and you have multiple layers all wired together, you can get very complex behavior because there's a lot of different possibilities for all the weights between all those different connections. Finally, we'll talk about a modern deep neural network, and really this is all there is to it. The rest of this course we're just going to be talking about ways of implementing something like this. Okay, so all we've done here is we've replaced that step function with something better. We'll talk about alternative activation functions. This one's illustrating something called ReLU that we'll talk about later. The key point there, though, is that a step function has a lot of nasty mathematical properties, especially when you're trying to figure out their slopes and their derivatives. So it turns out that other shapes work out better and allow you to converge more quickly when you're trying to train a neural network. We'll also apply softmax to the output, which we talked about in the previous lecture. That's just a way of converting the final outputs of our neural network, our deep neural network, into probabilities from whence we can just choose the classification with the highest probability. And we will also train this neural network using gradient descent or some variation thereof. There are several of them to choose from, and we'll talk about that in more detail as well. Maybe that will use autodiff, which we also talked about earlier, to actually make that training more efficient. So that's pretty much it. In the past 5 minutes or so that we've been talking, I've given you the entire history, pretty much, of deep neural networks and deep learning. And those are the main concepts. It's not that complicated, right? That's really the beauty of it. It's emergent behavior. You have very simple building blocks, but when you put these building blocks together in interesting ways, very complex and frankly mysterious things can happen. So I get pretty psyched about this stuff. Let's dive into more details on how it actually works up next. So now that we understand the concepts of artificial neural networks and deep learning, let's mess around with it. It's surprisingly easy to do. The folks behind TensorFlow at Google have created a nice little website called playground.tensorflow.org that lets us experiment with creating our own neural networks. And you don't have to write a line of code to do it. So it's a great way to get sort of a hands-on intuitive feel of how they work. So let's dive in. So head over to playground.tensorflow.org and you should see a screen like this. You can follow along here or just watch me do it, but I definitely encourage you to play around with this yourself and get sort of a intuitive hands-on feel of how deep learning works. This is a very powerful thing if you can understand what's going on this web page. So what we're trying to do here is classify a bunch of points just based on their location in this 2D image. So this is our training data set, if you will. We have a bunch of points here, and the ones in the middle are classified as blue, and the ones on the outside are classified as orange. So our objective is to create a neural network that, given no prior knowledge, can actually figure out if a given point should be blue or orange and predict successfully which classification it should be. So think of this as our training data, okay? We know ahead of time what the correct classifications are for each one of these points. And we're going to use this information to train our neural network to hopefully learn that stuff in the middle should be blue and stuff on the outside should be orange. Now here we have a diagram of the neural network itself, and we can play around with this. We can manipulate it. We can add layers to it, take layers out, add more neurons to layers, whatever you want to do. Let's review what's going on here. So first of all, we're selecting the data set that we want to play with. We're starting with this default one that's called circle. The inputs are simply the x and y coordinates, the vertical and horizontal position of each data point. So as our neural network is given a point to classify, all it has to work with are those two values, its horizontal position and its vertical position. And those start off as equally weighted, being horizontal or vertical. So we can define the position of any one of these points in terms of its horizontal and vertical position. For example, this point here would have a horizontal position of -1 and a vertical position of about -5. And then we feed it into our network. You can see that these input nodes have connections to each one of these 4 neurons in our hidden layer. And we can manipulate the weights between each one of these connections to create the learning that we want. Those in turn feed into 2 output neurons here that will ultimately decide which classification we want at the end of the day. So keep in mind, this is a binary classification problem. It's either blue or orange. So at the end of the day, we just need a single signal, really. And that's what comes into this output here. Let's go ahead and hit play and see what happens. What it's going to do is start a bunch of iterations where it learns from this training data. So we're going to keep feeding it input from this training data set. And as it goes, as it iterates through it, it will start to reinforce the connections that lead to the correct classifications through gradient descent or some similar mechanism, right? And if we do that enough times, it should converge to a neural network that is capable of reliably classifying these things. Let's hit play and just watch it in action. So keep your eye on that image to the right there. All right, you can see that we've already converged on a solution. I can go ahead and pause that now. And pretty cool stuff. So you can see it has successfully created this pattern where stuff that fits into this middle area here is classified as blue, and stuff on the outside is classified as orange. So we can dive into what actually happened here. The thickness of all these connections represent their weights. So you can see the individual weights that are wired between each one of these neurons. We start off here. And you can see these are more or less equally weighted. Well, not exactly equally. Some of these are kind of weak. But what it leads to is this behavior in the middle. So we start off with equally weighted x and y coordinates. Those go to this layer here. So for example, this hidden layer here, this neuron is saying, I want to weight things a little bit more heavily in this corner, okay? And things that are like in the lower left-hand corner, not so much. And then this other one is picking out stuff on the top and bottom. This one's a little bit more diagonal to the bottom right. And this one's even more bottom right heavy. And if you combine these things together, you end up with these output layers that look like this, okay? And so we end up with these two blobby things where we're sort of giving a boost to things on the right and giving a boost to things that lie within sort of this more blobby circular area. And then when we combine those together, we end up with our final output that looks like this. Now this might look different from run to run. You know, there is some randomness to how this is all initialized. Do we actually even need a deep neural network to do this though? One optimization thing is to remove layers and see if you can get away with it. Maybe we don't even need deep learning. I mean, really, this is kind of a simple thing. You know, stuff in the middle is blue, stuff on the outside is orange. Let's go ahead and remove one of these neurons from the output layer. Again, all we need is a binary result anyway. Can it still work? It does. In fact, it's just as quick. So do I even need that layer at all? Let's go ahead and remove that final layer at all. Still works, right? So for this very basic problem, I don't even need to do deep learning. All I have here is a single layer. So this is just, it's not even a multi-layer perceptron. It's just a perceptron. Do I even need 4 neurons in there? Well, I think maybe I do, but this one here isn't really doing much, right? All it's doing is basically doing a pass-through, and the inputs coming into it have been weighted down to pretty much nothing, so I bet I don't even need that one. Let's get rid of it. Still works. Isn't that kind of cool? I mean, think about that. We only have 3 artificial neurons, and that's all it takes to do this problem. I mean, compare that to the billions of neurons that exist inside your head. Now, we probably can't get away with less than that. Let's go ahead and try to do 2 neurons and see what happens. Yeah, that's just not going to happen, right? So for this particular problem, all you need is 3 neurons. 2 won't cut it. Let's play around some more. Let's try a more challenging data set, okay? So here's a spiral pattern. And you can tell this is going to be harder because we can't just say stuff in this corner is going to be this classification. Like, we need a much more finer grained way of like identifying these individual spirals. And again, we're going to see if we can just train a neural network to figure that rule out on its own. And well, obviously 2 neurons won't cut it. Let's go back to 4. Let's see if that's enough. I bet it isn't. Yeah, you can see it's trying, but it's really struggling. We can let this run for a while, and you can see it's starting to kind of get there. You know, the blue areas are converging on some blue areas, and it's really trying hard, but it's just not enough neurons to pull this one off. Let's go ahead and add another layer. Let's see if that helps. You can see it's doing more complicated things now that it has more neurons to work with, but still can't quite get to where it needs to be. Let's add a couple more neurons to each layer. Generally speaking, you can either add more neurons to a layer or add more layers. It's going to produce the same results, but it might affect the speed in which it converges, depending on which approach you take. It's just fascinating watching this work, isn't it? All right, this one got stuck. It still can't quite pull it off. Let's add one more layer. This is actually a very common pattern you'll see. You start off with a lot of layers at first, and you kind of like narrow them down as you go. Okay, so we're going to go to a initial input layer of 6 neurons to a hidden layer of 4 neurons, and then a layer of 2 neurons, which will ultimately produce a binary output at the end. Ooh, I think it's getting there. Here we go. Wow. Okay, so technically, I mean, it's still kind of like refining itself, but it kind of did it, right? I mean, now this is what we would call overfitting to some extent, you know? I mean, obviously it has these like tendrils that are kind of cutting through here, and that's not really part of the pattern we're looking for. It's still going though. Those tendrils are kind of getting weaker and weaker. So, you know, it still doesn't have quite enough neurons to do exactly the thing that we would do intuitively. But I mean, still, I mean, this is a pretty complicated classification problem. It figured it out. It may be overfitting a little bit, but it figured it out. And all we have is, what, 12 neurons here? I mean, that's insane, right? Now, another thing I want to talk about here, too, is that it kind of illustrates the fact that once you get into multiple layers, it becomes very hard to intuitively understand what's going on inside the neural network. This gets kind of spooky, you know? I mean, what does this shape really mean? I mean, once you have enough neurons, it's kind of hard to fit inside your own head what these patterns all really represent. I mean, the first layer is pretty straightforward. You know, it's basically breaking up the image into different sections. But as you get into these hidden layers, things start to get a little bit weird as they get combined together. Let's go ahead and add one more, shall we? Actually, let's add 2 more to this output layer and add 1 more layer at the end. Let's see if that helps things converge a little bit more quickly. Yeah. All right, starting to struggle a little bit. See that? Like, it's actually got a spiral shape going on here now. So with those extra neurons, it was able to do something more interesting. We still have this this little spike here that's doing the wrong thing, and it can't seem to quite think its way out of that one. If you gave it a few more neurons, though, it might be able to figure it out. These ones are also misclassified, but I find it interesting that it actually created a spiral pattern here on its own. So maybe with a few more neurons or 1 more layer, you could actually create an even better solution. But I will leave that as an exercise for you. Now that you know how to play around with this, I really encourage you to just mess around with it and see what kind of results you can get. This spiral pattern is, in particular, an interesting problem. Just to explain some of the other parameters here, we're doing a classification here. That's what we're going to be doing throughout this section. The activation function, we talked about not using a step function and using something else. Some other ones that are popular. ReLU is actually very popular right now. Realization function we haven't talked about yet. The learning rate is just basically the step size in the gradient descents that we're doing. So you can adjust that if you want to as well. Let's see if ReLU actually makes a difference. I would expect it to just, you know, affect the speed. Oh my gosh, look at that. That's pretty darn close to what we want, right? I mean, there's, apart from this little tiny spike here, which isn't really even there, there's a little bit of overfitting going there, but we have basically created that spiral shape just out of this handful of neurons. God, I could do this all day, guys, and I hope you will too. You know, just play around with this. It's so much fun, and it gives you such a concrete understanding of what's going under the hood. I mean, look at this hidden layer here. That's where these spiral shapes are starting to emerge and come together. And when you think about the fact that your brain works in very much the same way, it's quite literally mind-blowing. Anyway, mess around with this. It's a really great exercise, and I hope you have some fun with it. Hey, I hope you enjoyed this video and maybe learned a thing or 3. If you'd like to learn more with me, please check out the link in the description below. I have a whole larger course on data science, deep learning, and machine learning with Python there. It's very popular and highly rated, so I hope you'll check it out. And you'll also get a really nice discount on it by using that link in the description there. Anyway, thanks for watching, and I hope to see you again soon.